I think there's time next week. Okay, here we go. So this is your first week of Redox. Unfortunately, it's only on the recitation guide. Your lab is purely kinetics. I know, I thought it was over, and it's not. But the fun thing about this one is it ties together for you how acids and bases moved into kinetics, you know? So expressing how we go from using these things in a reaction-based setting and finding out how those reactions affect things like picking an indicator or picking which reaction you're going to use. So, first some housekeeping. As you know, there's no recitation tomorrow, which means that the pre-lab is not tomorrow because it's a reading day. Please do something fun with yourselves. I know you all have so much to do, but definitely take an hour to realize that you actually don't have to be doing something at this moment. It's a complete day of just relaxing. Whether that means sleeping in, I don't know. But do something for yourself. I guarantee you will want to. Next, the pre-lab is due on Thursday, not Tuesday. And then of course the lab then is due on Sunday. But the quiz is going to be on Wednesday and the homework is on Friday as per usual. So please remember that everything is as per usual except for the pre-lab and lab. So there still is going to be a quiz on Wednesday. I will of course be working on Tuesday. So please feel free to come see me and come ask me things like, oh, hey Victoria, I don't understand this. It's going to be on the quiz. The quiz will be kinetics based. So putting the heads up that it'll be mostly about half-life with a little bit of kinetics in there. Okay, speaking of kinetics, this is your lab of goals. I'm not going to read them to you because you are all old enough to read, but I am going to tell you that the basics of this thing is to find these rate orders for these two things based on varying the concentration. Something you did during the worksheet that was 2 weeks ago now is seeing how something changes in relationship to adding in a varying concentration or varying the time, etc. Like last week's lab. However, you're working with an indicator. It's called crystal violet and a base, aka our hydroxyl group. What you're going to see is that based on the rate, you're going to find an observed rate constant. That observed rate constant will first be based on the initial molarity of hydroxide. That is the same for the crystal violet. Why? Because the concentration of your hydroxyl is so much more than the crystal violet. So if you think about an indicator, you have like 3 drops. And it's still quite dark. Meanwhile, you have this hydroxyl group. It's going to be like a whole beaker full of stuff. So in that case, you can say that you're only going to find the K observed based on that hydroxyl group. So really based on the initial concentration of your hydroxide. I always add animations and I don't mean to. Now, how to do that is actually, so the K observed will be based on your hydroxyl group. But to find A, of course, you're going to have to base it solely on your crystal violet. So what you're going to do is see how the concentration of crystal violet versus time, and you're going to graph that, usually from 1 to 5 minutes. So not long. And through those 5 minutes, you're going to see how it changes. If that concentration versus time has a direct relationship, aka it's a straight line, then that means it's going to be 0 order. If you see it slanted downward, then that's going to be your natural log of CV versus time, then that means that's a first order. But again, you're looking for a straight line. If it's not a straight line, then it means it's not it. So if you see some weird curve, or you see some sort of mountain in the middle, I don't know, it's definitely not it. If you see a straight line, it means they're directly related in that sense, and that means they must be first, second, or 0 order. Does that make sense to everybody? That's clear? Okay. So, then you're going to examine your graph, because once you found A, of course you can find B, because as we know, A is not related to B entirely, it only helps us find B. So you're going to look at the concentrations. You're then going to say, okay, I've got my K observed, and then you're going to look at the rates that you get. And then you're going to compare the K observed that you see, because you're going to get an observed reaction constant. And you're actually going to compare them as if they were the reaction rates. So what I'm talking about is, you're going to take your observed rate constants that you see and relate them to the concentration of your hydroxyl group to then find B. It's the same as if when you compare the rates, just this time you're going to be seeing your observed rate constants. Does that make sense to everybody? I know it sounds like not what you've normally done, it isn't, but it's not like it's completely out of it. It's just using now two K values instead of the rates. But they still have to, of course, correspond to that experiment, right? So if we take experiment 3's observed reaction rate and divide it by the observed reaction rate of T1. We're going to then take it to the concentration of experiment 3 over the concentration of experiment 1, and then find B, right? And we always remember that B is like X or Y, whatever that equals will be our rate order. So if this was, say, if K obs of T divided by K obs of T1 was going to equal to 2, and then I took the concentration of T3 divided by the concentration of T1, and that equaled 2, then I know that the B must be 1. Does that make sense when I say it like that? Better? Amazing. Okay. Any questions about that? Any questions at all? Essentially what you're going to do is you're going to look at 2 beakers of crystal violet. Again, that's like 6 drops in water, not a lot, to 3 molar NOH, really concentrated. You're going to pour them in. You're just going to watch them change color. That's how fast the reaction is going. It gives you the concentration now of crystal violet. Again, like I said, super low, not very high. And then we see as it goes forward, it slowly becomes more and more clear. Again, as you and I know, without stirring, this is how long it would take actually an indicator to change color. And so slowly you see that one side is becoming more clear than the other. And then when you look at 5 minutes, you're going to take the time and the concentrations of each. Whoop. And you're going to say, okay, now I know what it is. Okay? Does that make sense to everybody? Yeah? Great. Okay. All right. Moving on to this very long recitation guide. All right. So the first thing you need to know is I have a lovely acronym. This lovely acronym lets me know exactly what's going on in terms of oxidation and reduction. It is called oil rig. You may have heard it before. If not, now is this lovely time to give you a little nugget of knowledge. Oil rig literally means oxidation is loss and reduction is gain.
Victoria, I thought you could use the one Leolda, that one as well?
No, that one's too long. This is short. I like short things. Not saying your teacher's wrong, just saying that one's too long. And reduction is gain. So, what I'm saying, losing what, gaining what? We're talking about electrons. So this is the loss of electrons. This is the gain of electrons. So, the only way that this gets confusing is when we talk about oxidizing agents and reducing agents. Because oxidizing agents are reduced. Why? Because they're so good at reducing that they help other things oxidize. That's why they're called an oxidizing agent. So they are reduced themselves, reduced to help oxidize is what we say in shorthand. So essentially, because they're so good at they're so good at being reduced, they influence other things to be oxidized, right? Because things that reduce gain electrons, which means they're taking them from somewhere, right? Lewis and acid bases, the wonderful Bronsted-Lowry definition. It's the same idea, but instead of hydrogens, we're talking about electrons. So because that oxidizing agent is being reduced, it's going to take those electrons, and what it's gaining is taken from somewhere, and whatever it's taking from is losing them. And if it's losing them, it's being oxidized. Okay, the reducing agent is the same thing, except obviously reverse, in that it is being oxidized to help reduce. All right, so same idea. It's so good at oxidizing it, losing electrons. It doesn't want any of them, that it gives them basically to someone else without even wanting them. They're like, I don't need the electrons. It's like, no, but take them. And then they're like, okay, and now they're being reduced without even wanting to be. That's what a reducing agent does. Okay, moving on. I'm going to zoom in a little bit. I feel like we're a bit too far. All right, so what is the oxidation number in the atom of the following situations? Well, first things first, when I look at neon in and of itself is a free element. If I look at number 3, free elements have an oxidation number of 0. Anything that's by itself, this equals 0. And I'm going to put a dash through them just because we're looking at oxygen next, and this is going to keep our zeros from our oxygens separate. When I look at oxidations of O2, now I'm going to say, well, if I have a neutral compound, then the oxidation number must be 0. I have O2, and then if I think about it, O2, it's probably, if I had to think of 2 things added together that equal 0, the only thing I can think of is 0. So I'm going to say that the oxidation number of this whole compound, there's no charge on it, so it's going to be 0. the next thing I look at is the carbon in methane. And if I look at methane, I'm going to say, okay, I have to look at rule number 4 now. And I read along a little bit, and it says hydrogen with non-metals equals +4. Carbon is not a metal, as we know. And so that means that I have 1 times the charge on carbon plus 4 times plus 1, which is the charge on hydrogen, is going to equal 0, right? Because this is no charge on it, so it's a neutral ion. When I think about that, if I put +4 on the other side, that's going to make it equal out. So if I put this, it would be -4, right? Simple math. If I have +4 on this side, I'm going to subtract 4 over here. 0 subtracted by 4 is -4, so C equals -4. Right? Everyone sees that? Simple? Great. C and C in this carbonate ion. So we have an ion now. That means that it doesn't equal 0. It actually equals -2. And so that means that anything I get is going to have to equal to -2. So I'm going to have 1 times that charge on carbon again. Do not assume it's -4. We have no idea. And that's going to be added by 3 times the charge on oxygen. Now I look down to my 4th rule again. I read along a bit further. It says, okay, oxygen equals -2, except when paired with fluorine or peroxides. It's not paired with fluorine or peroxides, it's just paired with carbon and oxygen itself. So that means that this is going to also be -2. And so if this is -2, that's -6, -2 plus 6, right? Because if I took this over, I'd have to add 6 to both sides. -2 plus 6 equals a +4. There we go. Now we know the charge on that carbon in that carbonate ion is a +4. Everyone follows me on that, right? That's simple math. Wonderful. The reason I'm going fast, you missed it because you came in a little bit after I had my little rant, but this thing's a long recitation guide, so we're just going as quick as we can. All right. Number 4, determine the oxidation number of the elements in each of the following compounds. So now we have this carbonic acid. So basically, we're just going to do what I did up here, but I'm just going to write it all out. So I have 2 times the charge on my hydrogen, plus the 1 times the charge on my carbon, plus 3 times the charge on my oxygen is going to equal again a 0, because this is a neutral ion. Like we said, number 1, if you have a neutral compound, the oxidation number must all add up to 0. So, going back through, again, we go back to our rules. This hydrogen with a non-metal is going to be +1. Carbon and oxygen are non-metals, so that makes sense. That's a +1. I read back to my oxygen. It equals -2, except when paired with fluorine and or in hydroxide. Again, it's paired with a hydrogen and it's paired with a carbon. None of that's a hydroxide to me. If you're looking to wonder what peroxides are, it's when you have a hydrogen that's paired with 2 oxygens. Like, we think of something that has those alcohol groups, those OHs, right? But by themselves. So like water, we don't treat like that, okay? I say OHs. It has to be O or HO2. There has to be 2 oxygens in there, not water. I'm mixing up things. It's been a long day. Okay, so this is going to be -2 then. And if I have -2 and +2, but this is times 3, so this is actually a -6. -6 plus 2 to get 0. This is going to have to be +4. Okay? Make sure it all adds up to 0. And it does. Now we have nitrogen. But again, like we learned with O2 up above, if you have free elements, their oxidation number is 0. That is the same here. And also it says if you have a neutral compound, the oxidation must add up to 0. Since they're both the same, it's a neutral compound. We know that the nitrogen in here, 2 times blank, and it equals 0, must be 0. All right. Moving right along, we have an ion now. An ion means that everything's going to add up to -0. So I have 1 times the charge on zinc plus, look down here, I have a 4. Don't forget your 4. 4 times the charge on my oxygen plus 4 times the charge on my hydrogen. And that is going to equal a -2. Okay. Everything so far so good. Now, hydrogen and oxygen still have the same thing as up here, right? We have oxygen -2 except paired with fluorine and peroxides. There is no peroxide. I only see 1 oxygen in there. So this is going to be -2. Again, hydrogen when paired with nonmetals, oxygen is a nonmetal. It's going to be +1. So here we go. Now I need to make this all add up. I've got -8 plus 4 is going to be -4. So if I have -4 between these, and this is -2. If I add 4 to this side, basically, I'm then going to get +2, and that's going to be my charge on my zinc. And then it makes sense, right? +2 -8 is going to be -6. -6 plus 4 is -2. Checks out to me. All right, moving right along, NO2 minus. So we've got, again, another ion. So I've got 1 times the charge on my nitrogen plus 2 times the charge on my oxygen equals a -1. Again, oxygen paired with nitrogen is still a non-metal, so then it's going to be, is still not fluorine, is still not a peroxide, so it's going to be -2. If I have -2 times 2, that's -4. -4 on one side. If I add 4 onto that other side to balance them out, it's going to be -1 plus 4. -1 plus 4 equals +3. So this charge on this nitrogen is going to be +3. Again, the way that I check that is I just look up above and I say 1 times +3 is +3, +3 plus 2 times -2 is +3 minus 4, +3 minus 4 equals -1. Tick, I'm on my way again. All right, the final one is just to point out that hydrogen is not always +1. Like we said, hydrogen with non-metals is +1. Hydrogen with metals or boron is -1. And so when I look here, I have 1, I didn't write this right, 1 times the charge on lithium plus 1 times the charge on hydrogen is going to equal 0. The thing here is that lithium is a metal. It's an alkali metal. And if you have an alkali metal, it means that suddenly now you're working with something a bit different because, as well, it's group 1. And group 1 is always, without a doubt, going to be +1. So if this is +1 and we need to equal 0, you better bet that my hydrogen is now a -1. All right. I feel like I'm selling cars or something, like I'm in an auction place. Please let me know if I'm going too quickly. I also need to remember to breathe. All right, here we go. Identify what's being oxidized, reduced, the oxidizing agent, and the reducing agent. So what I'm saying of this is, like I was saying way above, you notice what's being oxidized, directly beneath it, reducing agent. Keep it simple for yourself. Don't try to make this hard about going back and trying to remember which one, because I guarantee it'll just mix you up. So just go right back, right when you write oxidized, comma, reducing agent. Right? Okay. I'm going to do a quick example of that. In fact, 3 quick examples. So, basically, we kind of do what we did with the Bronsted-Lowry acids and bases. I just identify the pairs. So I'm going to circle my pairs. I've got tin that goes together and my chromium that goes together. I'm going to say chromium, when it goes from +1 to +3, it's becoming a lot more positive. For something to become positive, it must lose electrons. So this is the one that's being oxidized. And so if this is the one being oxidized, you better believe that this is our reducing agent. Okay, next you've got tin, 4+, now becoming tin, 2+. If something goes from 4+ to 2+, it's becoming more negative. It's not as evident, but it is becoming more negative, because if you think about it, a positive charge of 4 is a lot greater than a positive charge of 2. So if it became more negative, it must have gained electrons, which means then it's the one that was reduced. And if it's being reduced, then you can best believe that this is then the oxidizing agent. All right, happy with that? Great. Let's move on to this one. I've got mercury, I've got iron. All right, when I go from mercury 2+ to mercury in a compound, that mercury is going to equal to 0, like we've said above with N2 and O2. If I've got 2+ to 0, it's becoming more negative. I've gone from a positive to no charge. So that means it's becoming more negative. If it becomes more negative, it means it had to have gained electrons. If it's gaining electrons, it must have been reduced. If it's being reduced, it's the oxidizing agent. Next, we can kind of guess that this means that iron is going to be our oxidizer and therefore the reducing agent. We're just going to check. I go from Fe, that is a 0 charge on there because it's the pure element. Then to 3+, so I go from 0 to 3+. Okay, I am getting positive. If I'm getting positive, I must have lost electrons. If I lost electrons, I must be oxidized. And if I'm oxidized, that means I'm the reducing agent. All right. Next, what we're going to do is we have adenine, and when we have this, we realize that we actually have a sort of mini compound within here. And so what I have to say is that Cl- is also -1, but minus 1 times 3 is minus 3, so to make this all equal 0, this will be plus 3. Here with Cl2, I have 0, so on this Cl it's 0, and on this oxygen it's also going to be 0. So you have zeros and zeros on each side, but again, one became more negative and one became more positive, so we've still got the same stuff. So when I look at acid in here, it becomes more positive. If something becomes more positive, it must have lost something. If it lost something, that means it must have been oxidized. And if it's oxidized, it means it's the reducing agent. Next, I have chloride. Chloride, of course, is neutral, and I have something neutral. Now it's becoming minus 1. So it's obviously becoming more negative. We can see the negative sign. It's becoming more negative. It must have gained electrons. If it gained electrons, it's being reduced. Or sorry, yeah, being reduced. And if it's being reduced, that means it's the oxidizing agent. Oh, everyone's clear on everything that I've just said so far, even though I've said it a million miles an hour. We're good. Okay. Next, moving on. Okay. 6. I have an iron metal. It's being oxidized in the presence of O2. It's saying, would you expect the iron oxide to have a higher or lower oxidation number? We don't even have to really work out this problem, because whenever we see oxidizes, right? You and I know oxidizes is the loss of electrons. And if we lose electrons, that means that we're becoming more positive. So, if we're becoming more positive, it means we already expect that the oxidation number will become higher. And the reason for that is because iron metal has an oxidation number equal to 0. So if we have an oxidation number equal to 0, we can only go higher or lower. And since we're being oxidized, it means that we're becoming more positive. So we can only go up. There's no way to go back down. Does that make sense to everybody? Yeah? Great. Okay. Finally, based on the following reaction is C2 plus or zinc 2 plus. So I have copper and zinc. Which is the stronger oxidizing agent? Well, we don't have to panic. All we have to do is figure out who's the one being reduced. Whoever's being reduced is probably the stronger oxidizing agent. No? That makes sense to me. So, I look here. I've got zinc with a 0 charge. I pair that up with my zinc 2 plus. 0 to 2 plus, okay, I'm becoming a bit more positive. If I'm becoming a bit more positive, this means that if I'm becoming more positive, it means I must have lost electrons, so I'm being oxidized. So this is my reducing agent. And that must mean that then I have copper 2 plus becoming copper with a 0. So it's become more negative. It's being reduced. So therefore, this is my oxidizing agent. Right? That makes sense to me. Okay. Let's move on to the next one. All right. Write 2 half reactions for the following and identify which one is oxidation and which one is reduction. Okay. So, first things first, we know, like we've been doing up above, we just separate our species. I have Mg solid is to Mg2 plus. I have Fe3 plus is to Fe2 plus. But I have to balance these. I have to realize, I'm like, okay, well, wait a minute. These aren't balanced. I've got 2 different charges on each side. And now I look through and I say, okay, I have this 0 to 2 plus. So to balance that charge from neutral to 2 plus, I have to add on 2 electrons onto this side. Same thing down here. I have Fe3 plus. This is plus 1. More than this side, so I have to take off 1 positive charge by adding an electron on that side. Now that I've set them up completely and they're completely balanced, I look up here and I say, okay, how am I going to identify which one is oxidized and which one is reduced? Well, like we've said from the very get-go, oxidation is loss. Reduction is gain of electrons. So between the 2 of them, the one that is gaining electrons is going to be this one. It has it in the product side. It's being added on to our final product. Meanwhile, in the top one, my final product is that plus electrons. So we lost electrons in the overall reaction. So this side is being oxidized. Does that make sense to everybody? We all see that. How if you have electrons as a product, it means that it's going to leave the system. It's now on the inside. But if I have an electron on my reactant side, I'm being added into the reaction now. So I'm being gained by whatever I'm with. Does everyone see that better? Does that make more sense? Hopefully when you have this lecture, it'll make tons of sense. That's my actual hope. All right. So now it says put the balancing redox reaction steps in order. So basically, this is for stuff that's in acidic conditions, so the order is not going to matter for the basic ones that we do, but we can still write it down. So basically, the first thing you want to do is you want to make sure that you write the half reactions. So you have your oxidation and your reduction half reactions. So you're going to do B. Then you're going to balance everything that's not an oxygen and not a hydrogen. Okay? Next, what you're going to do is balance the oxygen singularly by adding on water. Finally, you're going to balance the hydrogen because you, again, just added a bunch of water. So then you're going to balance your hydrogen out. Finally, you're going to balance the charge because, again, you just added on a bunch of protons. So then you're going to balance the charge. Then you're going to multiply them to make sure that you get rid of all those electrons because you can't have any of those in the final cut. And then you're going to check for balance, which I'm going to show you how to do. Essentially, when you check for balance, that's your one way of saying, did I do this right? If you didn't do it right, you'll know when you check for the balance. And then I suggest the steps you go back to look at are the hydrogen step and the oxygen step. Those are the two where people usually miss something. Okay. Time to balance our very first redox reaction. This one, luckily, is quite easy because a few steps are not necessary. So, step 1, I write out my half reactions as they are. So I have zinc is to zinc 2 plus, and I have silver plus is to silver solid. Okay. Step 2. Step 2 is, okay, I would need to balance anything that's a non-hydrogen, a non-oxygen. I look here, there's no such thing. There's no oxygen, these are all balanced. 1 and 1, 1 and 1. No need. Step 3. Okay, I need to balance my oxygens. I look here, there's no oxygens. Nice. No need for that one. Step 4. I need to balance the hydrogens from the waters I added. I didn't add any waters, so I don't need to do that. Great. Now, step 5. This is where we balance our charges. So, I have zinc is going to zinc 2 plus, but it needs to have a 0 charge overall, so I add on my 2 electrons. I have silver plus, so I need to add on 1 electron to become silver solid. Now, someone asked me, this is a very good question, why didn't I do that first? And the reason we don't do that first is because we're going to add on protons, and we're going to add on oxygens before that, and the protons are a part of balancing the charge. So we want to do that after step 4, okay? So when you first split your half reactions, do not put in the electrons, because you're going to have to do it again after you add in your protons. So I like to do it after adding in the protons. You'll see that in the very next one, where we actually have to add in protons, okay? Just trust me for this step, okay? Is that cool with everybody? I saw no positive signs of life out there. No one nodded at me. Okay, step 6. Now, I'm going to multiply to make sure that I cancel out my electrons. So, luckily these are quite low numbers, and I can see that the first one, if I multiply by 1, I'll be okay. And at the bottom one, I multiply by 2, they'll cancel out. So, I multiply the top one by 1 per se. We don't really need to do that, like write it out, but I like to make it all very clear. And the bottom one by 2. And then for step 7, we're just going to cancel them out. So I have zinc is to zinc 2 plus 2 electrons. And then I have 2 silver ions plus 2 electrons is to 2 solid silver. I add together. If things are on opposite sides of the arrow, they cancel. So in this case, my 2 electrons. And what I'm left with is 2 silver ions plus zinc is to zinc 2 plus 2 solid silver. Everyone happy with that? So the one thing to make sure is that you cancel everything out. The next one is going to be really evident of that. So we're going to have waters and hydrogens and electrons. Now, like I said, the final thing we got to do though is check that we balanced it. This one I'm pretty certain of because there was no hydrogens or oxygen adding. But if you look here, you've got 2 times plus 1 plus 0. So you've got a plus 2 plus a 0 charge. So this equals plus 2 overall. You've got 2 plus 2 times 0. So then you've got a plus 2 on this side. And that equals, so that checks out. Okay? So that's the one last thing to do. This is nice because you can see it quite easily, but it's much better to see when we go into further sections. Like, the one thing to remember is any neutral compounds are going to be 0, so you don't have to go trying to add up stuff. Like if you see H2O, you don't have to go minus 2 and then you plus 2 hydrogens, whatever, plus 1 charge, blah, blah, blah. It's like, no. H2O overall will be 0, so you can just say that's a 0. Okay. Now to go in for the doozy. Here's the much longer acidic one. Oh, I need to be in screen still. Where we're going to actually have to use, as you can see, some oxygens are in there, so some hydrogens are going to have to be in there, etc. So, we still start as always. Step 1, I'm going to write out my half reaction. So I have I2 solid becomes IO3 minus, and then I have NO3 minus becomes NO2, which is a gas. Great. Next step, you balance all the non-hydrogens and non-oxygens. And so when I look here, the only thing that needs balanced in this one is oxygen, so I don't have to worry about that one. But in this one here, the iodine is not balanced. So I'm first going to balance my iodines. So I have I2 is to 2 times that IO3 minus. And then I have that NO3 minus is to NO2. Okay, step 3, balance your oxygens. So first we're going to balance the oxygens by adding in water. So, first things first, I see I've got 6 oxygens in that iodine reaction. So I'm going to have I2 plus 6 H2Os is to 2 IO3 minuses. Here I have an NO3 minus is to an NO2 minus. And so I know I'm going to have NO3 minus is to NO2 plus 1 H2O. Great. So far, we're off to an okay start. Okay. Step 4, I have to balance those hydrogens now, right? I've just done the oxygen stuff, now I have to balance my hydrogens. So what I'm going to do, making sure I'm on screen, is I'm going to say, okay, I have 12 hydrogens. So I have I2 plus 6 H2O is to 2 IO3 minus plus 12 H plus. Woo! That's a lot of hydrogen. That's a lot of acid. And then I have 1 H2O over here, so that's 2 hydrogens. So I'm going to have NO3 minus plus 2H plus is to NO2 plus 1 H2O. The reason I'm carrying through the 1 is only because what we're about to do, obviously, which is first we're going to add in our electrons. So I want to see how many hydrogen ions I had to add, because it's 1 times 2. And then we're also going to be in step 6, then multiplying them and canceling stuff out. So it's just good to see the coefficients that we sometimes don't write. Okay, step 5, as I promised, this is where we're going to add in our electrons. The reason we always do it at step 5 is because I'm actually balancing the charge of the added hydrogens in there. So I just added in 12 whole hydrogens. So I have 12 1 plus on this side. And this side, and a 2 minus. And this side is completely neutral. I've got I2, that's 0, and H2O, that's 0. So we've got a lot of balancing to do. So if I have 2 minus and 12 plus, to get 0, I'm going to have to add in 10 minus signs to get to 12 plus with my already existing 2 minus. So I have I2 plus my 6 waters is to 2 IO3 minus plus my 12 hydrogens plus 10 electrons. For this one, I have neutral and neutral, and then I have 2 plus and 1 minus. So if I want to get neutral, I'm just going to have to add in another electron to balance out that charge. So I have 1 electron plus my NO3 minus plus my 2H plus is to NO2 plus my 1 water. And like I said, now we're moving into that final step, multiply and cancel. So I'm just multiplying to get rid of my electrons, nothing else. And so when I look at this, I say, okay, there's 10 electrons on top and 1 electron on bottom. So the only one I need to multiply through is this last one. I mean, you can technically do the top one, but it's going to be the same. But this one will be times 10. All right? So step 6, we're going to multiply that through, and I get I2 plus 6 H2Os is to the 2 IO3 minus plus my 12 H plus my 10 electrons, and the bottom one is going to be 10 electrons plus 10 NO3 minus plus 20 H plus is to 10 NO2 plus 10 H2O. All right, and finally, our final step before we check our charge and see if we've done all these steps correctly is I'm going to add them together and cancel everything that's left. So, my 10 electrons of course cancel. That's what we're aiming to do. I have, oh wait, what's this? Yeah, 20 H's. Where's my other H's? 12. And they're on opposite sides of the arrow, so that's good. My 20 becomes 8. My 12 gets completely canceled. I'm just going to make complete cancels here just so they look a bit more completely canceled. I have 10 water and 6 water, so that's going to become 4 waters, and this will be completely canceled. And I think that's it. I think I've done everything. All right, time to write it out and see if we did it correct. So I have I2 plus 10 NO3 minus plus 8 H plus is to 2 IO3 minus plus 10 NO2 plus 4 H2Os. All right, just a little off camera. Now, here we go. Time to find out. I2, that equals 0. 10 times negative 1 is negative 10. H plus is positive 8. This becomes negative 2 plus 10 times 0 is 0. Plus 4 times 0 is 0. Okay, I reduce this one down. This becomes minus 2 plus 0, so that's nothing. And this becomes minus 2 plus 0 plus 0. Minus 2. We've done it. This is correct. Whew. We've got one more to show you. And then I feel we need to just go home and take a break. But this one will be in basic solution conditions. So it's the longest one you will have to do. I doubt it will be on a quiz because it's so long. It will take the whole quiz, if not longer. It might be on a worksheet, so I can't make any promises. But I can say I don't think it'll be on a quiz because that would just be mean. Or they do half of it for you. So, with that being said, not to scare anybody. Whew. Okay. So, step 1 is the same as always. I write them out, and I'm still going to suggest that we don't balance anything. So I've got Ag is to Ag2O and then Zn2 plus is to Zn. And then my step 2 is still the same, in that I say, okay, I have 2 silver, so I need to multiply this side by 2 to then get my Ag2O. And then my zincs are balanced, so they're okay. And then my third step is still the same. I need to add waters to make sure that everything balances out okay, so that's all fine. Oh wait, there we go. So this is going to be 1 oxygen, so 2 Ag plus 1 H2O is to Ag2O, and my zincs are fine. Next, okay, I added in water, so like we said before, we need to add in hydrogen. This is why the basic solution one is so long. We've added in hydrogen, but when you think about it, we're in a basic solution. Hydrogens are not so easy to come by. So later on, we're going to have to add in hydroxyl groups to neutralize our hydrogen. So this is why we don't like these problems, is this step right here. So I'm still going to add in my hydrogens because it's harder to not. So I'm going to have my 2 Ag plus my 1 water is to my Ag2O plus 2 H pluses. And then if I have 2 H pluses, I also have to have my zinc one, which is untouched, thank goodness, so we only have to do this once. Now I have step 5. Step 5 is adding the charge, and like I said, we always add based on the whole charge. So here I have 2 plus on this side. This is a neutral compound, so this is 0, 0 and 0, so this is 2 plus, so I'm going to add 2 electrons on this side with my hydrogen. So 2 Ag plus my 1 H2O is to my Ag2O plus my 2 hydrogens plus 2 electrons. And then of course I have my zinc 2 plus 2 electrons is to zinc. Great. I would say we'd have to multiply things together, but luckily the 2 electrons cancel out, so we don't have to do step 6. So we move on to step 7, where we add them together. I'm going to add them together, and I say, okay, just my 2 electrons cancel out, and everything else gets pulled down. So I have 2 silver plus 1 H2O plus my zinc 2 plus becomes my Ag2O plus the zinc plus my 2H plus. Again, unfortunately, we're in basic conditions, so that H plus can't stay there, which is where we move on to what they call step 8. In that, I now have to add on hydroxyls in the same amount as H plus to neutralize them. So I'm going to add on 2 OH minuses, and then I'm going to combine them into water. So I have 2 Ag plus H2O plus zinc 2 plus is to silver oxide plus zinc plus, and then again, we combine these together to get 2 H2Os. And then my final step is I just say, okay, I have 1 water on one side, I have 2 waters on the other, so I cancel them out, and I say, this water's got to go, and this one gets reduced to 1. And so I get in my final step 2 Ag plus my zinc 2 plus is to my silver oxide plus my zinc plus 1 water. Okay? And then, as always, we can check. And we can say, did we do this correctly? Something's missing. What's missing? Oh, Yes, because this is charged. Good. 0, this is +2, this is -2, so this is my +2, and this becomes neutral, neutral, check, check. Okay, we're not doing the next one. So as you can see, there's oxygens, hydrogens, and it's going to take us 20 minutes. So I'm going to post it on your PSO page with all the steps, so you don't have to do it with me, but if you need to do it with me or have questions, please feel free to email me, we can go through it. Okay? I'm going to let everyone go home, marinate on this loop-back to redox reactions. It's so fun. If you have any questions on pre-lab, lab, homework, maybe you got a quiz, I will tell you as much as I can, obviously, answer the C and all that, and then I will see you next week. We're going to do redox with some organic chemistry. And then, of course, I see you for one more week, and then it's on to finals. And I'm going to just be holding office hours all week. Okay? So you're almost there. It's the home stretch. Good luck. And I'll see you next week.
That was quite long when I did it all out. It was quite long to write all those steps out.
So long. So long. And then I looked at the next one, and I felt so bad for the class I was teaching because I was like rushing through the last few steps. And I'm like, I don't even know why I'm teaching this because I'm not teaching you. I'm just scribbling it really quickly. And then we do this. And then we do this. And then one girl was like, I'm just going to record you, okay? And I was like, that's fine. I was like, I record you too because I'm just talking so quickly. So anyway. Yeah, this is long. These are the long ones because with basic solutions, you can't have any H plus left over, so you have to like neutralize. That's the only move for it.
Yeah, like canceling things down, writing things all over the place. It's like a lot of writing.
Yeah.
They're not expected to do this on the quiz if there isn't.
Not the basic one, the acidic one, yes, but more like that first one I showed you, where like you skip steps. You know what I mean? So
They
then
don't want
expect
it to take too long, I guess.
Yeah, the ones that don't take too long. Because obviously they want you to learn, but also it's like what you test you on, and you get a wide range of topics. Because we don't want to just test you on this, you know what I mean? Because it's stuff that you came into a quiz, it's like, what's step 1? What's step 2? You're just actually doing it in multiple steps, when in reality it would be nice to just have 8 questions that are a broader range. Okay, anyway.
Why is AG2O positive 2?
Because that Ag is our positive 2, and that O is negative 2, because it's bonded to not chlorine and not oxygen. And so we treat it as an ion. But only in basic solutions, because we are assuming it's going to break apart.
Okay. I also have a question on the free lab.
Awesome.
For this thing.
0.
Yeah. Thank you.
No problem. I know that's confusing.
Yeah, it feels like 0.3 is the whole number. It's not like that.
0.
Yeah.
No, there, I think we mentioned this before, that doesn't show correct for you, because they sometimes don't, you say a whole number, and sometimes they put a whole number to mean something else in Caltech.
Yeah.
And then you accidentally wrong, and you have to like reset everything, and sometimes something you want to reset. So that's why sometimes you feel like you got it right, check with me, because then I can also zoom in and just reset the whole system going to different reset.
I was surprised on the last lab and the one that had to do with the timer. Why didn't have the timer show up?
I know,